In section 8.5, we're looking at vectors. A vector is any quantity that has a magnitude, that's a size, so it tells us how long it is, and a direction. We often see these in physics where maybe we have a force pushing in a certain direction. It tells us how strong the force would be and which direction it's going. It could also be a distance, like how far we're walking in a certain direction or something like that. Every vector has an initial point, a starting point, and a terminal point, which we have an arrow on the terminal point to show us where we're going. We write a vector like this. Notice the arrow there is only a half arrow because we don't want to confuse this with a ray. A ray would keep going indefinitely, but a vector is stopping here at D. Sometimes vectors will be put into the coordinate plane, and when we do that, we'll represent it with an ordered pair. Now notice that it's not an ordered pair with the parentheses that usually give us an xy. Instead, what it's telling us is how far over we're going for x and how far we'll go over for y, and so that we use chevrons instead of parentheses. So we're going over 2 and up 4 for that. Notice then that we would have the same vector name 2, 4 for any vector that's going over 2 and up 4 no matter where I put it in the plane. Often we'll put it starting at the origin to help understand it so that the endpoint would be the point 2, 4, but we don't always want to do that. Now if I turn this around, notice that I could also have it going this way. Now I'm going backwards 2, so negative 2, and I'm going down 4, that would be a negative 4. In this one we want to describe a vector. Notice we're given an angle off of the x-axis. Now to do these, we usually want to put them at the point 0, 0 to start out with. Now this length of 65 here is our hypotenuse of this triangle, so notice that we can use sine, cosine, or tangent because this will always be a right angle. The 65 then is our hypotenuse, the y is opposite of our angle, and the x is adjacent to it. And so if I'm looking at the cosine of this, that's going to involve x adjacent over the hypotenuse with our angle of 50 degrees. The sine of our 50 then will involve the y opposite over hypotenuse, and then we can solve each of these for x and y. Now those are our values. Those are telling us the length of x and y, and so we can write this vector as, first of all, x. Notice we're going in a positive direction. Now I'm going to round this to the nearest tenth. But notice that y is actually going down. Even though I have a positive number, we need to look at the picture here. This is a negative 49.8. Now describing a vector direction, the way that they'll do that in this book is they look from what direction we're going. So if we're going east here, but notice that we go south of that. So measuring from the east line, they would say this is 25 south of east. Or this one here, it's mostly going north, so they're saying that it's 35 degrees east of north. Okay? But notice that we could have also described this one as coming from south. Since this is 25 degrees here, then that would mean that this side is 65 degrees. So we could say it is 65 degrees east of the south mark. Or this one over here, if we think about measuring from the east, how far north is it of the east? Well, that would leave us with 55 degrees north of east. So we can name it either way. Usually they would put the smaller angle to describe it. The resultant of a vector is when we add two vectors together. So in this picture I have a vector u followed by a vector v. Think about it that I decide to walk whatever my vector u is, and then I walk what my vector v is. I would be following from my endpoint. Now I might often have those vectors in different places, but to find the resultant vector I would put them together end to end, and then to find where a new vector would take me, I would just draw a new vector connecting my starting point with my endpoint, and that will be my vector w. Now this might be something like if u is the direction that an airplane is flying, but the wind is blowing like blue, then that airplane is actually going to fly in the direction of w because it's being pushed by two different forces. If we see this in a coordinate plane, then we can just add our x's and y values. We could see this by starting with the red at 0, 0, if I'm doing u plus v, and then I could move it over here, and we see that the endpoint here would be, my resultant vector would be connecting those endpoints and giving me w here. So to get my resultant vector, I would start by adding my x's, 2 plus 3, and I would add my y's, 4 plus a negative 1, or 4 minus 1, giving me a resultant vector of 5, 3. Notice the endpoint here is at the point 5, 3. Also, it doesn't matter which order I add these. Let's say that we had started by going with v and then laid u on the end there. It would end up in the same place, and we would have the same resultant vector for w. On this page, what we see is a canoe that's in the water. In the canoe, the people are paddling in this direction, but the current of the water is pushing them in this direction. So the actual motion of the canoe would be along this blue vector. And so if I have a river and we're trying to row across the river, if I'm focused in this direction, I'm rowing in this direction, but the river is going in this direction. So I'm moving at 31 miles per hour, 35 miles per hour, but the river is pushing me at 8 miles per hour. I'm going to end up actually following along the hypotenuse of this. So if x is this angle here, we want to find out what angle it is that we're looking at here. And we also want to know how far we're actually going to be able to go. What is our resultant speed, basically? So first we're going to look for our resultant speed, which would be our hypotenuse here. We can set this up using the Pythagorean theorem. C squared is equal to 35 squared plus 8 squared, which will give us about 36 miles per hour. And we can use trigonometry then to find out what this angle is, to find out what direction we're actually going. So we're using tangent because we're using the 8 and 35. We could use this 36, but it's good to use the given values because they're probably more exact. And so 8 over 35, we can solve that using the inverse tangent, and we get an angle of about 13 degrees. So our direction is 13 degrees south of west, okay, because we're moving west, but we're being pushed a little bit south. There's our directions there. And our speed is about 36 miles per hour.